We like to be able to show students how to organize knowledge. And this is based on the principle that how students organize knowledge influences how they learn and apply what they know. Now, by organization, I'm really thinking in terms of major topics and subtopics. Now, this is almost like a really hierarchical view, and this is how instructors often think about these. These are the major topics, and then these are subtopics. That's not necessarily how students view this material. As an example, from 2020, this is the syllabus from 2020. This is what you see. Here's the major topics right here. And then those are the subtopics under each one. Students oftentimes just see this as a whole list of topics, and they don't identify the organization here. And I know this is a fact because in my class, I once gave them extra credit for turning in their notes for a particular day. Now, the best students in the class had this sort of structure. In fact, when I teach the class, I underline things and I say, big titles, headings. I'm very careful about the organization. And there were still some students in the class who missed that and their notes didn't reflect it. So you can imagine if you're studying for a test or a student is studying for a test and this is the view that they see, they're not going to be able to do that well on the test or fully understand the material. So to help them, again, make sure that your notes are very clear about what the structure is. Another way to go a little bit deeper in this is concept maps, where not only do you have the major topics and subtopics, but you show this concept map that shows how they relate to one another. As an example, let me look at concept map for 2020. Again, we have these major topics, and then under each one, these are the subtopics. But then we show this relationship by them. So switch systems really goes back to transistors and how we build things out of transistors. And what we say here, the relationship between Boolean algebra and switch systems is that Boolean algebra expressions can be implemented in switch designs. They can also be implemented using gates. And the other thing is gates. Gates are composed of specific switch transistors. So in other words, these are the major topics, and then these are how they relate to each other. So that's a concept map. In a study guide, when I give them or talk about a study guide for each topic, each major topic, be able to come up with what do you have to do. So be able has to do with skills, and then know has to do with knowledge. So for each topic, this is what you have to do, and this is what you have to know for them. So I relate this all together when I do a review. So a standard review for a test, some people go through and they go through this structure. This is what we covered, the major topics, minor topics, and this is what you should know. So they do that, but that's a very passive way. What we want to do is have the students be able to organize this knowledge themselves. So I want to do a little bit more active about this. So I'm going to do two options to standard reviews. One of them is a two-step approach, and introduce them to the idea of a concept map and study guide, the ones that I just showed, the concept map and the corresponding study guide. And show them how to do it for test one, because they've never done it before, so you have to give them the guidance. And then for test two, have them do it. For homework, they say, come prepared for class, we're going to have this test, I want you to do your own concept map and study guide for this test. And then when they come into class, have them break into groups and discuss their maps with others. And that takes maybe about 20 minutes. And then after they've discussed it and they've modified theirs, then you show yours. So what you require them to do is sit there and organize their knowledge of the material and try to figure out what's important, what's not important, what the study guide should be. And now the time. So this takes about 30 minutes because they've done most of the work beforehand. You don't spend too much time going over yours. And compare that to a standard review. Standard review for a test, you oftentimes take 15 to 30 minutes anyway. And so if you're saying this is passive, you're just saying stuff to them and they're not really activating their memory or organizing material themselves, versus this, where they are forced to do the organization and get some feedback from other students and from you, whether they did it correctly. So this is a more effective way of doing it. Now option B, and this is a fun one to do, and it's very insightful for you as an instructor to do this. Tell them, okay, we're going to have a test. Suppose I'm going to ask you only 3 questions on the test. What topics or what question types would they be? I've done this. And so I write on the board when they give me the answers. And a circuits example, I might get like mesh analysis problem, or some people say node analysis problem with Devinant. And then I'll have others say things like, oh, it might be a KVL problem or an Ohm's law problem. And I even prompt them. I say, I'm only giving you 3 questions. And they'll still say things like Ohm's law. I'm not going to waste a whole question on Ohm's law. And that tells me that some of those students don't really understand this concept of the major topics and minor topics. And so then I explain to them after I write down all these examples why I might ask some versus the other. I say Ohm's law, you have to understand Ohm's law to do a KVL problem. And you have to understand KVL to be able to do mesh analysis. So what I'm more likely to do is ask you the high-level mesh analysis problem because that encompasses all these other things. And there are students in the class that look at me like, wow, that's what a revolution. But you can tell the better students in the class and the most successful automatically do this. It's the bulk of them, or this large percentage of them, that need to be trained how to do this. I want you to think about this as or link it to the class as thinking like an engineer. We do organized thought processes, major topics, subtopics, and how they relate. For example, in engineering design, we think in terms of systems and subsystems and the integration. Engineering analysis, the major effects and minor effects, and how it relates to performance. Studying for a test, major topics, subtopics, and how they relate to each other. Note-taking, major headings and minor headings, and highlighting the important parts. Time management, major task and subtask. We inherently think like that because we're trained engineers. The students are novice at doing this. So encourage them and link it to this whole organized thought process. Link it to being a good engineer. All right, thank you.